as Faye said, I work with TPAC in the applications group. Specifically, I'm very interested in developing high-speed PWI FMC immersion applications, in particular using adaptive technology. So I'll be giving I have a lot of slides. I'll click through some really quickly to avoid boring people until I get to the results, the pretty pictures at the end. So just a really quick overview of who TPAC is. We're a unique team in NDT. We're about 70 people around the globe right now. We're really kind of two brands in one company, AOS and TPAC. Some people are confused by this. AOS is the bare boards, electronics inside that can be integrated. And TPAC is when we essentially integrate those ourselves into an end user product and software application. But we really work hand in hand together. This is an array of our bare boards up top, package solutions below, and various softwares we've developed underneath. This is the part where I kind of come in. I work in Westchester, Ohio, outside Cincinnati. I'm an applications engineer in the back. I have a very nice immersion tank with 9 axes, XYZ, gimbal swivel, probe swivel, turntable, bar roller, automated lift table. Really, we've invested in trying to develop applications for aerospace and other industries with this nice equipment. I'm sitting up at my perch there. And prior to that, we had a small immersion tank, about 1 meter cubed, that I did some work with, and we still continue to use for smaller applications. And one of my colleagues and myself use a UR cobot to do a lot of development as well, of demonstrating what you can do with a UR instead of an immersion tank. This was just a good representation of 34 of us representing the company in Korea last summer at World Conference for NDT. And we're a global presence. So a quick overview of FMC TFM for those who might need it. Some do, some don't. So phased array UT is a conventional beamforming technique where we predefine focal lulls and fire timing delays on multi-element arrays, whether they're linear or matrix, and can predetermine the angle of our emission or a focal point of our emission. And the important point of this technology is that in conventional beamforming, what we call conventional phased array at our company, is that the focal lulls are calculated on the device and the reception beamforming is calculated at the device level. So the analog A-scan signals are captured, and then one beam is formed from a subset of A-scans and transmitted from the device to PC, to software, whatever you want to do with it. This means essentially that you have to predetermine your focal point and predetermine your firings for your delay lulls. So moving beyond that into advanced phased array, FMC, TFM, these terms are thrown around a lot. There's really 2 parts to it. The first part is the acquisition scheme called full matrix capture. And this is an acquisition scheme that's carried out in the instrument doing the analog part of the work. Total focusing method is the image reconstruction afterwards with all that raw A-scan analog data and turning it into an image that our eyes can interpret to be very meaningful, because looking at the raw A-scans with my eyes is very confusing, but the TFM algorithm does a great job of making it meaningful. So really quick, FMC scheme is fire one element, receive all elements on the probe. So that's what the red and blue is representing here. And as you add more elements to your array, the amount of data that you produce can multiply very rapidly. So it's for a 4 element, you get 16 waveforms. For 64 element, you get 4,096 waveforms. Most of the work I'll be showing here today is from 128 scheme, so 128 squared A-scans. This is just an animation of those firing sequences. So we fire one element on the left, and on the right, we're receiving the reflection on all the elements. And on the left is showing what the receptions from the first element fired and received on element 1, the first element fired and received on element, say, 32, the first element fired and received on, say, element 64, if it was a 64 acquisition. And this next block here is saying if you fire on the next element, or element number 16, these are all those receptions from all 64 elements from left to right as A-scans. This is the image that's not particularly meaningful to my eyeballs. So we store all that information in an array, so we know which element we transmitted from and which element we received on, and we have all these A scans. Another way to look at that matrix is like this, as it was on the green screen before, or like this. But what's the interesting part? Well, the interesting part is we can say, underneath that probe where we've done all this firing and reception, let's define a grid of pixels that we want to draw, and draw a representative amplitude of all the signal that reached those points and was received in reflection from those points. So I'm not going to go into the math, but excuse me. There's many algorithms that you can use to calculate this data. Delay and sum is probably the simplest of those, and that's the one going to be talked about the most today. So delay and sum just means essentially you sum the amplitude at this point of the A scans that represent being at that point at that time. So the power of this is chaos to my eyes, but the TFM algorithm says it looks like this. This is very good SNR, very good resolution. So the important point to stress here is in conventional phased array, you have your device, you do your beamforming in the system, and you get a resolution because you pre-focalized your beam laws, your delay laws. If you're doing FMC TFM, you have your device, you fire your A scans, you collect them, you send them, and you process them through an algorithm using a GPU in our case, and can get this kind of resolution out of that. And the advantage is this can be focused everywhere, because when you want to draw this point, you choose the A scans that represented that point in time. So a faster way to do FMC is called plane wave imaging. And plane wave imaging is, again, a acquisition scheme where instead of firing one element, we fire all elements, so a large aperture. And then again, with the same receiving on all elements, we carry out a image reconstruction or post reconstruction method. So FMC is fire one element, the blue, and receive all the elements. PWI is fire all of them, and you get a plane wave going outwards. And if you do that with different delay laws across the probe, you can fire an angled wave or a plane wave. And if you do that multiple firings at multiple angles, you can then take all those receptions and average them. So this time our matrix is that each angle that we fired and the A scan received on each element. We do the same TFM algorithm on that, and we can produce a TFM image with high resolution as well. So this is a bit of a comparison between TFM and PWI. This kind of should say FMC versus PWI, I apologize. So FMC is fire one, receive all. It takes longer. There's more work to be done. It's a lower acquisition speed and a lower computation speed, but a higher resolution and a higher contrast. Plane wave imaging is a higher acquisition speed, faster computation speed, and you still get good resolution and good contrast, but not as good as FMC. So it depends on what your application and end goal is, kind of an important choice on which one of these two techniques that you'd want to utilize. Yes? Data size. FMC is much bigger raw A scans, but the computed TFM image is the same size. And I'll have some stats on that, actually. That's okay, good question. So the next part of this is, that's interesting on a situation where we tell it where we expect the wedge to be, or the immersion water path to be, and where we expect the test subject and material to start. But what if we didn't know that? What if the curvature of the entrance of our system was not flat? Well, we can actually not know the surface ahead of time and use the Fermat principle. And I'm not going to do the math or explain this. It doesn't matter. You just need to see the pictures, the result at the end. The optimization is based on the Fermat principle, but we can say at that point in space that we want to draw, what must have been the simplest solution of the source of the A scans in order to have the best result. And what happens there is, again, we do this TFM reconstruction on a pixel grid. And scanning through, for example, this curved part, with standard TFM, where we aren't accounting for the surface not being flat, we get this terrible image. If we adapt and interpret what the surface must have been, we get this image. This is another example of adaptive TFM on what we call a wavy block. So we just have we have this demo at our booth if you stop by to see it. So we have some wavy surface and some various holes, some various reflectors in here. And with a water-filled bladder wedge, so an adaptive water bath, you can go over top of this. It will conform to the surfaces and represent these images properly. This is the same thing going through a weld crown with the water wedge shown. There are various types of adaptive wedges being actively developed right now by different companies too. Instead of just a water bladder, there's now some soft polymers and things. So one question before I go any farther, I get asked a lot of time. Most of my data is going to be from aerospace on like plate or billet scanning. And people say, why would you do this adaptive thing on these boring geometries of a rectangular plate or a round billet? You know the shape. Why spend the time to do the adaptive? This is my answer I came up with for those people. One, there's actually two videos of this in a row that I'll share. Usually has a pretty good impact on audiences. So this is a piece of two metals welded together. There's some geometric features before they were welded, and there's a weld joint in here. And there will be some weld flaws right here. And I have predefined the water path to be 50 millimeters. And we can see all these geometric features clear as day and our weld flaws clear as day. But now I'm going to raise the probe in the water up to a different height and lower it to a different height. So I deviated my water path. So I've deviated my pre-calculated focal walls. And what happens is these features both blur and unfocus, as well as what's much more important to me is the distance between the front wall and the features becomes misrepresented if you watch this go up and down. And that's really bad. But if we come over here to adaptive PWI, now I'm raising the probe up and down, and it's just figuring out where the water is and where the metal is, and it's adapting the focal wall live on the fly and keeping everything in focus and everything at the proper depth. So when I made this one, it's a nice, pretty graphic. It has a lot of features to see. But the next one, it wasn't quantified of how much I was moving up and down. So in aerospace, on plate, there tends to be like a 1/4 inch water path allowance, where across scanning a whole plate, they're allowed to deviate plus or minus 1/4 of an inch of water, and the scan is okay. So I want to show what happens if we do 12 millimeters or a 1/2 inch of water path deviation with adaptive versus non-adaptive. This is a number 2 flat bottom hole inside of a titanium calibration block. So phased array, conventional phased array kind of suffers a similar fate to what this does. If you don't have the right water path, your focal walls are wrong, and you won't even see this if you deviate very far. But adaptive doesn't care where I put my probe. As long as I allow enough A-scan before and enough A-scan after my intended inspection window, the algorithm can compute this and keep it all in focus and draw it properly for us. So these are more application examples. So the picture on the left is stainless steel, 6 inches deep, 4, 5, and 6 inch deep, number 3 holes. The right side is near surface resolution. Those are number 1 flat bottom holes in titanium at 1.5 millimeter. And there's some very good separation in S&R here from the front wall on this guy. So a good example of how deep we can go. This is a set of number 2 flat bottom holes in titanium between 1.5 millimeters and 6 inches, or 60 thou and 5.75 inches. Each one of these blocks was scanned with TFM, and I built a DAC, or a TCG. It's really a DAC in this case and not a TCG, to gain each one of those reflectors at those depths to 80%, plus or minus 1 dB. And the reason this is an animation is each one of those blocks was a separate entity. So this is a stitched together image of each one of those being stacked on top of each other. So what kind of power can we see here? Well, these titanium individual DAS blocks, distance amplitude set blocks, at 3 different depths, near surface, mid, deep, with that DAC calibrated for each one of those to be 80%. And this is a different titanium calibration standard, also with number 2 flat bottom holes at different depths here. These are a similar depth range to this, and using the same calibration where these are calibrated to 80% and they're hitting, you can see the difference in the background grain structure of this titanium plate versus these titanium bar stock. The noise level is much higher here in this rolled plate than it was in this bar stock. So this is the type of thing that the FMC can really bring out and show. This is a 4-inch thick set of 3 cow blocks of stainless steel. These are number 3 flat bottom holes between 1/8 of an inch and 3.9 inches in 4-inch thick stainless. And this was an animation of each one of those cow holes as a static B-scan image. This is a video of after I've done that acquisition and built that DAC to do that 4-inch depth range, which is very interesting. So a lot of the times scanning this plate in practice, there's kind of a practice of scanning the first 0 to 2.5 inches and then flipping it over and scanning the other 2 inches because there's a lack of resolution. So this is one acquisition from one side, all 4 inches, using a large probe at 8.8 inches squared per second of surface coverage. The scan on the left, the C scan on the right top. So over here we can see the live image under the probe as we went, and we can clearly see all of these cow holes separated. I will share that the reason for this noise here is a gap between these blocks, because there's actually 3 blocks sitting there. So still cross-section, merged view through the thickness. This is the C-scan top view. This is the narrow end view. This is the length view. So this was the first encoded axis. This is the second encoded axis. We can see all of these flaws from 3 millimeters or 1/8 of an inch to 3.9 inches in this 4-inch block with very high S&R. So that scan that I just showed you was running FMC TFM, so not PWI, FMC TFM, the slower kind, plus the adaptive algorithm, which slows us down even more. And I measured the effective beam width of those cow blocks to be 5.26 millimeters at the shortest for a -6 dB. Used a scan step of 70% of the effective beam width, so 3.6 millimeters. If we were to do this scan on a 12 foot by 4 foot plate, 4 inches thick, I could run that scan in 14 minutes of acquisition time. And the amount of A-scan data that I've flooded between my device and my computer is 1.1 terabytes. The volume of data that I have reconstructed with the algorithm to draw the result is 17.5 gigabytes. This can be saved locally. I do not recommend saving the 1.1 terabytes. We can save this, and what we end up with here is not just a C-scan, it's a 3D voxel cloud. It's a 3D representation of reconstructed image of your part. And you can go in and remask it and remerge it and redraw it. Basically, essentially redraw infinite number of gates through it. However you want to draw gates through it is kind of the best way to put that. So this is where we calibrate to 80% and we gate the C-scan at 40% and we sample at minus 6 dB effective beam width. And we probably are going to and maximizing each indication if we found something during the scan. And it took us 15 minutes to do the scan. So this is going to reduce the scan time, but if we need to go back and analyze anything we find, we're going to increase the analysis time. So what if we wanted to try going the other scheme? Let's scheme this a different way. Let's say I want to do a minus 1 dB scan step. I have to slow down my scan because I need to sample at a tighter interval, 1.7 millimeters. But that same 12 by 4 plate, I could scan it in 30 minutes and have 2.5 terabytes of data this time that I threw out when I was done with it and collect 37 gigabytes of data. The good news here is we can get the scan done in a longer time, but do we really need to go back and go to and post-analyze everything if we had 1 dB variation in our sampling? That's a question I pose to those who actually do the production techniques. I don't know the best answer. And the good news, the bad news here is currently we're kind of limited by the RAM on a graphics card, and a 5090 GPU is 32 gigabytes, and you get about 25 usable. So you'd have to break this into 2 sections to store it. For now. We'll be developing writing to disk so that we don't have to do that. This was proof that that worked. So I did 4 scans of those cal blocks using the 6 dB sampling and the 1 dB sampling, plotted the calibration hole amplitude in the resulting C-scan, and the error bars from the 4 scans. Everything is above 40 here. And this is the 1 dB sampling, 80 to 92%. Again, why use adaptive? A plate is flat and boring. You scan a 3-meter plate and then look at the front wall. A 3-meter plate is a rolled thing. It's not actually flat. So those focal laws here are wrong compared to those focal laws here. This is another example. I don't think I'm going to go spend time on it, but this is where we could actually find microstructure flaws using the adaptive TFM and FMC data, and then track down with process engineering where this microstructure growth that was localized to one side of a plate and in one region of a plate, where it came from in the process, and correct that problem. This is titanium billet. I don't want to talk too much, but this is 8.5-inch titanium billet with number 2 flat bottom holes. And these are 5 millimeters to 130 millimeters, whatever is just past half depth of this billet. This is adaptive FMC TFM. This is that whole merged voxel cloud and a cross section of the length. These are the number 2 cowl holes. This should be an animation. See if it, here we go. It's a drawing of the calibration standard, making it really clear what we're seeing. And this is the SNR of those holes. So this is not in dB, this is in ratio. And they were between 4 and 9 at those various depths to that titanium billet. These are those individual holes on that tie billet analyzed. And this is showing some different schemes of how we would use this linear array to do this, and how we can get nice, really good SNR, or we can get worse SNR, and I'm not going to spend time here. I'm going to wrap it up. So thank you all for your attention. If you'd like to learn more, please do stop by our booth at TPAC and ask us, and I'm happy to fill in all the details. I have a live demo of this software running. And thank you for your attention.